I'm Patrick Lamb, and I'm going to talk about putting the semantics into semantic versioning. This is joint work with my co-authors, Dietrich and David Pearce. Software reuse is here. ModuleCounts.com says that there are over 1 million packages in the NPM ecosystem, which provide functionality for people to use. In other ecosystems, there may not be millions, but there are certainly still hundreds of thousands of packages that are available. These packages come with a cost, however, and the cost is the endless treadmill of upgrades. Upgrades are dangerous, and as a downstream developer using some external dependency, you're caught between the whirlpool and the rock. The whirlpool of endless upgrades, you can never really stay ahead of upgrades. The rock of, well, you ignore problems and then they come and smack you in the face. How bad can it be? You can ask former Equifax CEO Richard Smith about that. Among other problems, his software was not upgraded on time, and that caused personal information of millions of Americans to be leaked onto the internet, which resulted in an invitation to testify before Congress. You might think that you can avoid this by upgrading early. That can be tricky. One way to think about this is as upgrades as technical debt, but debt that just accrues with the passage of time. You don't have to do anything to accrue this technical debt. Now, as a software developer, you have a lot of priorities to juggle, and technical debt is only one of them. It may, in fact, be more important for you to add features to your software as well as remove your own bugs. And technical debt only matters if you don't go bankrupt. Instead, what we would like is for upgrades to be easy. Well, if not easy, at least less painful. So let's talk a bit about semantic version numbers. We're not going to give a formal semantics, but we will say what they mean informally. A semantic version number has 3 parts. It has a major, a minor, and a patch. When an upstream developer changes software in a way that should not be visible to users, but just results in it doing what it was originally supposed to do, then they would signal that by changing the patch version of the software. Sometimes upstream will add features, but not break any existing functionality. They would signal that by changing the minor version. Finally, sometimes upstream developers do have to change their software in backwards incompatible ways. They would signal that by changing the major version of the software. This is a way of understanding changes. And we can think about it as a form of simplified contract, which expresses some of the information you want to know about what changed in software. Semantic versioning is an ideal that may never be fully met. However, we can lower our standard, and if we do that, then there are many analysis techniques that can be brought to bear on the problem. Our thesis then is that the research community has a key role to play in developing relevant tools to help developers with upgrades. We think this is an important problem, and it's an opportunity for everyone to contribute their own expertise to making the world better for developers. To better help developers, I think it's useful to understand where they're coming from. And so I want to talk a bit about what happens when developers do upgrades. Let's look at this from upstream's point of view. The first question I want to talk about is, why does upstream cause breaking upgrades? Well, it's not true that ostriches put their head in the sand. It is true that sometimes developers don't know that they're about to make breaking changes. We found this to be the case in a number of software upgrades. It also happens, though, that sometimes developers decide that the right thing to do is, in fact, to make a breaking upgrade. Perhaps the requirements have changed. Perhaps the software is now to run on different hardware. There are reasons that developers choose to change the API and make previous software no longer work with their software. Another question to examine is, how do developers make breaking upgrades once they decide to do so? So there was a survey in FSC 2016 by Bogart et al. That surveyed different communities and their practices with respect to breaking upgrades. In the Eclipse community, the convention was not to make breaking upgrades at all. If you have an API, you are stuck with it forever. In the R community, the convention was that upstream told downstream about breaking changes, whereas in NPM, upstream had increases in major numbers to signal upgrades that would break. Now let's talk about a specific example of a breaking upgrade in the context of the web browser, Firefox, and the font selection library, FontConfig. What happened here was that FontConfig previously did not constrain blank file names and said it was okay. This was not specified in the API. And at one point, they decided to change their implementation so that blank file names would no longer be permitted. FontConfig actually does care a lot about breaking changes, but they figured it would be okay. It turns out it was not okay. This caused Firefox to fail to render text. The outcome here then was that FontConfig eventually backed off and once again made it okay to have blank file names. Now let's talk about downstream. So we talked about this a bit before, but I wanted to go into more detail. And so consequences of upgrading late, as I said, in the worst case, you get called to testify before Congress. But there's also the issue about technical debt and priorities, right? So you have external bugs and you have vulnerabilities. And so what happens is that if you want to get the upgrade from version n to n+1, which has the fix to the external bug, then you better already be at version n. If you are not already on top of the game with respect to version n, but are instead at version n-5, then you have to continue upgrading to version n before you can upgrade to version n+1. And so if that happens to be at a time that is not convenient for you, then you might have unhappy developers as a result. We also talked earlier a bit about why it's hard to upgrade early. And so again, it's a competing priorities problem. So to put it another way, you have things that are very obvious. You have internal bugs, and you also have future requests that you have to add. And there's clear incentives to do so. The incentive for doing external upgrades is much less clear. It's kind of the invisible man. And so very often, the more high priority thing is going to and should win. Upgrades, even in the best cases, can be playing with fire. You will have, ideally, some good continuous integration, and it's going to tell you things are going to break, but it's not going to be foolproof. You have static analysis, and it's going to miss things as well. So every time you do an upgrade, things might break. It also might be made worse by having slow infrastructure for compiling your new changes. You might ask, well, what about automated upgrades? Unlike the tooth fairy, automated upgrades are real. However, sometimes they also cause your code to break. And you can see a quote on the screen about how changes to dependencies can cause developers actual problems and sad life experiences. Now that we've talked about the context in which changes are made, let's talk a bit about how we can reason about these changes. And so we want to talk about contracts in particular and how we reason about programs in the presence of contracts. So there's a lot of tools in various states of development that check whether a program conforms to its contract. And you can kind of, in some sense, think of infer, redo, and quick check in this way. So this is useful. Also useful is understanding changes between contracts, contract versions. Both of these are required for understanding the impact of potential upgrades on software. I also want to talk about API surfaces. And so the question is, which changes are relevant to an upgrade compared with a particular client? And so to reason about that, one might think of using the open world assumption when reasoning about upstream, as in all the methods might get invoked. This is actually quite limiting in terms of upstream being able to declare that their changes are safe. In the limit, it says you can make no change to any public method, or if you allow reflection, no change to any method at all. So it's often useful to somehow limit the API surface and say, okay, there's a lot of methods, but only some of these methods might actually be called, and you only have to worry about those methods. Java 9 modules is one way of limiting the API surface, although it doesn't restrict it as much as we might like. We can also take a closed world assumption and, for instance, say, look, there are 4 clients that we care about, and only if our change breaks these 4 clients will we actually rethink our change. If you're not one of those 4 clients, then you might be in trouble. If those 4 clients are representative of all the clients, then you're good. Finally, at the limit, and from the downstream perspective, there's only 1 client. And so then there's a lot of potential changes which might not affect you if you're lucky. This is the opportunity, by the way, for incorporating modularity into programming language design. There's been a bit of work, but we think that there can be more. And this has a lot of benefits for enabling static analysis of various sorts. Having discussed why developers make breaking changes and the situation with upgrading, we'd now like to move our attention to the future and talk about our proposal for changes being classed in a taxonomy. We think that taxonomies are useful for different communities to discuss what changes they think are important to them. We proposed in the paper a sample taxonomy just as a starting point for discussion. We think that taxonomies are important because they can inspire tool developers to focus on certain areas which are not otherwise already covered. Furthermore, the taxonomy can serve as a starting point for a community to have a discussion about what social norms it's going to enforce. And certain communities may care about different things in terms of breaking changes than other communities. Having discussed the taxonomy, I now want to discuss tools and what roles they can play in our taxonomy. But first, returning to the context, once again, upgrades are a collaboration between upstream and downstream developers. In some sense, it's not fair. It's all the responsibility upstream to say what they changed, and then the changes flow downstream, and the downstream developers bear the responsibility for the changes that upstream makes. And so that causes issues. Semantic versioning is limited because it is not supported by any reasoning. And so industry has said, in some cases, that it's a lie not worth the business risk. Our vision is that upstream signals changes, which are verified using tools and conforming to a taxonomy in a machine-readable format. And then downstream is going to use these tools to verify declarations of breaking changes and check that the upgrade is compatible in its specific context. So about the role of tools, but before we talk about that, we should talk about pitfalls of tools. And they're the usual static analysis pitfalls, but customized to this context. So a tool might miss some breaking change, and that's obviously a problem. Or it might cry wolf too often, and then it'll just get ignored. As an example of a tool then, consider Rev API, which is an API analysis and change tracking tool. It is unsound and imprecise, and yet still it detects semantic version numbers that are incorrectly assigned to actual changes. Let's talk about some recent progress in tools and why we think that they can really help with versioning these days. There's been a lot of work in scalable static analysis, which can apply to realistic size libraries. This is using progress in incremental static analysis. And also fuzzing can help as well, get better understanding of what programs are actually doing. There's also been recently hybrid analysis combining dynamic and static analysis, which can help with both the optimism and pessimism problems. So to reiterate our overall vision, there should be information about changes which are certified by tools. This information is given to downstream along with the provenance, and then downstream checks it. So for instance, upstream might say, we checked our upgrade with Rev API and cross-version testing, and we found no breaking changes. And downstream can either believe that or rerun the test itself. We can have a shallow layer, a meta tool, which combines existing tools using, for instance, data log, and takes the output from all these tools and combines them into a single yes/no answer, or perhaps maybe. So now to conclude, our goal is to make dependency management easier. And we think that this is a particularly good time for doing so. There is a lot of continuous integration infrastructure available, and there's a lot of software projects which use this infrastructure. So it's easy to plug in tools into this infrastructure. There's also incremental analyses and other advances in program analysis tools that make it much more feasible to analyze large code bases than it was in the past. There are already existing program analysis as a service tools which look at changes that are committed to repositories and analyze them for properties of interest. So we would like to make a big tent call to action. We think that this is an important problem, and it's an important problem that many types of different expertise can be profitably brought to bear upon. It can integrate researchers in contracts, API services, taxonomies, and even human factors. We hope that you will join us in doing research in this fascinating area. Thank you.